Welcome to a new session on the massive open online course Introductory Concepts of Digital Computing offered by Swayam. In the last class, we learnt about the edge triggered D flip-flops. We designed it using three basic flip-flops. The advantage of flip-flops is that they can be synchronized since they obtain their output only at regular intervals of time. This commendable attribute of the flip-flop makes it highly stable and predictable. In this session, we will see another technique to trigger the flip-flop at the rising or the falling edge using master-slave flip-flops. So, let's start with the design of the master-slave flip-flop. Here, we have two flip-flops. One is master and the other is called as slave. The master-slave flip-flop can be built using SR flip-flop, D flip-flop and JK flip-flop. The concern about the indeterminate state of SR flip-flop still persists in SR master-slave flip-flop too. The D master-slave flip-flop has only one input and only two states, as it was having for the D flip-flop. The JK flip-flop was a solution to the above problems. Similarly, in the context of master-slave flip-flops, JK master-slave flip-flops outweighs other two. In this video, we will be focusing on the SR and JK master-slave flip-flops. We will begin with SR master-slave flip-flop and check the block diagram. There are two flip-flops that are similar. The only difference is in the application of clock pulse. One flip-flop receives the clock pulse as it is and it is the master flip-flop, and the other receives the inverted clock pulse, which is the slave. Moreover, note that the output of the master flip-flop is fed as the input to the slave flip-flop. At one glance, you can make out that both the flip-flops will not get triggered at the same time, since the same clock pulse is not supplied to the flip-flops. Rather, they receive the complements. Now, some questions need to be cleared before we proceed further. What is the logic behind this negation of the clock pulse? And why do we want to withhold the triggering of both the flip-flops at the same time? Let us recall some facts about the clock signal that we discussed in the previous class. We learnt that clock is a square form signal which has two states, high or low. As per the figure, you can see the clock duration. A clock period is measured in time from the start of the one positive edge of the clock to the start of the very next positive edge of the clock. In this duration, half of the time the signal is in high state or low state, whereas the edges appear only for an instant of time. Due to the nature of elements used to build these logic gates, there are some undesirable effects such as instability if the circuits can change their outputs for almost during their entire half of the cycle. What is the impact of the instability caused in the circuit? Recall the block diagram of a sequential circuit. There is a feedback path from the memory element back to the combinational circuit. If this memory element, in this context we are using the flip-flops, is triggered by the level of the clock pulse, then as long as the clock pulse is high, there will be continuous application of inputs from the combinational circuit to the memory element. This will in turn change the outputs of the memory elements for the duration of the clock pulse at the high level. Remember, this output goes back to the combinational circuits as inputs again. This causes instability and it is an unnecessary situation which can be avoided if the memory elements produce output only at a particular instant of time. That is, change the output of the flip-flop only at the rising edge or falling edge. This is the reason why we prefer edge triggered flip-flops. Now, keeping two similar flip-flops with negated clock pulse will suppress the working of one flip-flop either at the rising or at the falling edge. How? If the clock pulse is 1, the master flip-flop will work and the slave flip-flop will be inactive, and when the clock pulse is 0, the slave will work and the master becomes inactive. Since one flip-flop works as the feeder for the next flip-flop, we need to ensure that both the flip-flops need not get activated at the same time. This assurance is achieved here. Both the flip-flops does not change their output state at the same time and will not cause any undesirable effect. That's the reason why we are negating the clock pulse before supplying it to the second flip-flop. Now, let us study the design of the SR master-slave flip-flop. See the logic diagram given here? It has a master and a slave flip-flop and both have the same design. Look at their inputs. The master has two external inputs and the clock pulse, whereas the slave flip-flop has two internal inputs and the negated clock pulse. Where is this internal inputs coming from? They are the outputs of the master flip-flop, which are supplied as the inputs to the slave. Compared to the basic SR flip-flop, this master-slave flip-flop is active when the clock pulse is at low level 2. In the basic SR flip-flop, when the clock pulse is low, the flip-flop was inactive and it remained as a storage element which held the recent value of the flip-flop when the clock pulse was high. Now, it is the time to see the working of the master-slave SR flip-flop. We have already seen how an SR flip-flop works in the earlier sessions. If you have not seen those clips, then I highly recommend you to watch those videos to comprehend the concepts better. Do you remember the characteristic table of the SR flip-flop? Let us brush up our memory. Just look at the table. The values of S and R when clock pulse is positive is given there. The output is denoted as Q of t plus 1, which corresponds to the next state of flip-flop after applying these values as the input. In brackets, I have given the states of the flip-flops, they false to after applying these inputs. When S and R are 0, the next state of the flip-flop will remain the same, it will not be changed. When S equal to 0 and R equal to 1, the flip-flop will be reset, and when S equal to 1 and R equal to 0, the flip-flop goes to the set state. And both the inputs are 1, they will remain in an indeterminate state. Now, we have seen the characteristic table of SR flip-flop. Let us apply the same in master-slave flip-flop too. But remember, these output states were obtained only when the clock input was high. We need to see the other side too, that is when the clock pulse is low in the case of master-slave flip-flop. Let us start with clock CLK equal to 1 and S equal to 1 and R equal to 0. Since clock is equal to 1, the master flip-flop gets active. The logic gates of the master flip-flop will respond to the inputs S equal to 1 and R equal to 0. As per the working of SR flip-flop, now the master flip-flop turns out to the set state with Y equal to 1 and Y dash equal to 0. These are the inputs to the slave flip-flop. Remember, the clock pulse to the slave is 0 since the value is complemented and applied to the slave. What happens then to the slave flip-flop? It will remain in the previous state because the clock is 0. What was the effect of supplying the inputs Y as 1 and Y dash as 0 to the master slave flip-flop? Yes, indeed it changed the output state of the master flip-flop, but could not make an effect on the slave flip-flop since the clock was at low state. That indicates the application of the external inputs did not change the external output of the master slave flip-flop. Now check the scenario when the clock pulse goes down to 0. The external inputs are the same. What happens then? The master flip-flop has the clock input as 0, which forces the master flip-flop to remain in the previous state. What was its previous state? The flip-flop was in a set condition. The slave flip-flop now gets activated, the inverted clock pulse becomes 1 and triggers it. Now, what are its inputs? The outputs of master flip-flop y equal to 1 and y dash equal to 0 turns out to be the inputs of the slave flip-flop, that is s equal to 1 and r equal to 0 for the slave. Then we can make out the output of this slave flip-flop. It will set the flip-flop and turns the external outputs q to 1 and q complement equal to 0. You need to learn two important points here. One, on the application of external inputs and when the clock pulse is high, the master flip-flop changes its state, but this change of output is not reflected in the slave flip-flop. The second point is, when the clock pulse is low, the output produced by the master when the clock pulse was 1 is carried to the external output by the slave. So, as the term implies, the master controls the working of the circuit and the slave carries the value recorded by the master to outside. That is why they are called as master-slave flip-flops. Now, you take any combination of the inputs S and R, the above said phenomenon repeats. According to the external inputs, the master flip-flop controls the working of the circuit and the slave carries the value to the external output while the clock signal moves to its falling edge. You may work out the other combinations of the SR master-slave flip-flop to validate this. So, in a nutshell, the characteristic table of the basic SR flip-flop and the master-slave flip-flop is the same. The difference lies in the way the master-slave performs to remove the instability of this circuit caused due to the various reasons cited earlier. Now, let us move our focus towards the JK master-slave flip-flop. This is the most popular master-slave flip-flop as it eliminates the shortcoming of SR and D flip-flops respectively. How can we construct a JK flip-flop? It can be constructed using two SR flip-flops with the output of the slave connected back to the master flip-flop. Look at the logic diagram. See the master and slave flip-flops and note that the output Q of the slave flip-flop is connected to K gate of the master flip-flop and the output Q dash is connected to the J input gate of the master flip-flop. Another striking characteristic of the JK master-slave flip-flop is that it can avoid the race around condition which arises in the basic JK flip-flop. Do you remember what is the race around condition? When does it affect the flip-flop? It affects when both the inputs to the JK flip-flop are at the high level, that is J and K is equal to 1. We had learnt that the JK flip-flop succeeded in eliminating the indeterminate state of the SR flip-flop when both inputs were high. Now, the same combination of input is the cause of another problem. How can it happen? Let us pause and see how JK flip-flop has eliminated the indeterminate state of the SR flip-flop. It connected the outputs back to their inputs, forming a loop. This assured that one of the inputs to JK flip-flop will be 0. Why? We call the condition that output of the flip-flop should be complement of each other. So, one of the output from the circuit will be definitely 0 and hence one of the input will also be 0. That is how we solved the problem of indeterminate state of SR flip-flop, and the circuit toggled the output each time when both its external inputs were high. The same feedback of inputs which helped to eliminate the indeterminate state produced the undesirable effect of the race around condition now. What went wrong? The reason for that is if the clock pulse is set 1 for a long period of time, the circuit will keep changing its output. We have seen in the characteristic table of the JK flip-flop that when J and K are 1, it will toggle the value which flip-flop was holding. At one point of time, if the output Q equal to 0, then in the next moment it becomes 1, and this toggling continues as long as the clock pulse is 1. Such a condition of basic JK flip-flop makes the output unstable. This is known as race around condition and can be eliminated using master-slave JK flip-flop. Hope you understood the significance of the JK flip-flop, and let us see how does the master-slave JK flip-flop eliminates the race around condition. Let us recall the characteristic table of JK flip-flop. The JK master-slave flip-flop assumes the same outputs as described by the characteristic table. But as we have seen in SR master-slave flip-flop, the master responds to the change in external inputs at the rising edge of the clock pulse, and the slave carries the value to the external outputs while the clock pulse is at the falling edge. The rising edge changes the state and it only occurs for a fraction of time. The race around condition can be totally eliminated from the JK flip-flop. Whenever the inputs to J and K are low, the master flip-flop continues to be in the previous state at the rising edge and becomes inactive at the falling edge. At that moment, the slave carries that value to the external inputs Q and Q dash. You take any input combination of the JK flip-flop, the same procedure repeats. Now, I want to add 2 more points before I conclude. The master-slave combination can be constructed for any flip-flop by adding a clocked SR flip-flop and connecting the inverted clock to the slave. You can make the master slave of the D flip-flop too. The most popular is but the JK master slave flip-flop itself. The second point is that suppose you have a digital system with many master slave flip-flops connected serially, that is one after the other. In that case, you can easily synchronize all those master slave flip-flops using a single clock pulse. At the rising edge, all the masters become active and their outputs may change, but this effect will not reach the slave and in turn will not reach the next master slave flip-flop. When the clock turns to 0 or at the falling edge, all the masters gets disabled and now the slaves carry the data to the next flip-flop. But these inputs will not make any changes to the next flip-flop until the rising edge of the next clock pulse. This mechanism of changing the output at the same time is called as synchronization, which is a highly favorable characteristic of the sequential circuits. With this, we are winding up our discussion on the topic flip-flops. We started with the design of master-slave flip-flops. Master-slave flip-flops can be built by SR, D and JK flip-flops, where JK was detailed in this session. The elimination of race around condition was also covered. One of the significant characteristics is that it can be used for synchronization. Hope you got a clear picture about the sequential circuits and flip-flops. Few of the applications of sequential circuits will be discussed in the forthcoming sessions. Thank you for watching. See you in the next session. Bye.